Dear students, we have discussed two methods for performing a hypothesis test for a population mean. One is the Z test. If the population mean is known, if the population standard deviation is known. The other is the T test. If population standard deviation is unknown. These two procedures are based on the assumption that the variable under consideration is normally distributed, or that sample should be relatively large. For small samples, both the methods should be avoided if outliers are present and if the removal of the outliers cannot be justified. Now we discuss in this session a third method for performing hypothesis test on a population mean. It is known as one sample Wilcoxon signed rank test. One sample Wilcoxon signed rank test, or simply Wilcoxon signed rank test. It is a non-parametric test. And in the last class we have discussed in detail the difference between parametric and non-parametric methods. The test is based on the assumption that the population, the variable under consideration is symmetric, or the distribution of the population is symmetric. That is, if you divide the population into two pieces, one piece is the mirror image of the other piece. But to apply this test, normality assumption is not required. So this test is applicable if the distribution is normal because it is symmetric, uniform because it is symmetric, binomial because it is symmetric. So the only requirement is that population is symmetric. So can be applied to normal, triangular, uniform, symmetric, binomial, etc. But cannot be used if the distribution is skewed right or left. Whether it is right skewed or left skewed, this procedure cannot be used. So in order to explain this, let us consider an example. The example is the food cost for a typical US family of 4 is estimated to be $157 per week. That is the average food expenditure of a US family of 4. Now 10 Kansas families were randomly selected and the monthly food expenditure average monthly food expenditure has been noted, and we want to test the hypothesis whether the average monthly expenditure on food by a Kansas family, is a US state, is significantly lower than the monthly food expenditure of the entire US families. So our null hypothesis is mu is equal to 157 versus H1 mu is less than 157. Now the cost of 10 families is 143, 138, 169, 152, 149, 150, 135, 141, 161, 159, and D is defined as x minus 157. The difference minus 14, minus 19, 12, minus 5, minus 8, minus 7, minus 22, minus 16, 4, 2. Then absolute value 14, 19, 12, 5, 8, 7, 22, 16, 4, 2. Then rank of the absolute value is 9, 6, 3, 5, 4, 10, 8, 2, 1. Then the signed rank denote it as R is minus 7, minus 9, 6, minus 3, minus 5, minus 4, minus 10, minus 8, 2, 1. Suppose, these are very clear to you, suppose that now given this data, this is the monthly expenditure on food of 10 randomly selected Kansas families. We want to test this hypothesis, difference, absolute difference, rank, signed rank. Then the reasoning behind Wilcoxon signed rank test is like this. If H0 mu is equal to 157 is true, as the distribution is symmetric, we expect the sum of positive and negative rank to be roughly equal. Sum of positive and negative rank roughly equal because distribution is symmetric. And if you add these ranks, you will get it as equal to 57. So 57 by 2 is 27.4. So if you add the positive and negative ranks, it is assumed that positive and negative ranks will be roughly 27.5. And to put it another way, if the sum of positive ranks is smaller than or much smaller than 27.5, there is evidence that H0 is false. And monthly expenditure on food will be less than 157 for Kansas families. And in our example, the positive ranks 6 plus how many positive ranks? 6 plus 2 plus 1 is equal to 9. Positive ranks is much lower than 9. So the question is the difference between the observed and expected rank is due to sampling error, or is it due to the fact that monthly expenditure on food by Kansas families is lower than the entire US average? To implement this test, we have to use Wilcoxon signed rank table. This table is available with all the statistics books. And in the table, a W alpha will be given. W alpha will be given. That is the W values that has an area alpha to the right. W alpha will be given. An area say alpha is equal to 0.05 to the right. And the areas are given in the column headings. Now, entries in the columns are the critical values for right-tailed test. Right-tailed Wilcoxon signed rank test. For example, if you observe a particular value that we will see with an example, it is for right-tailed Wilcoxon signed rank test. But as the distribution of the variable W is symmetric, about n into n plus 1 by 4, n into n plus 1 by 4, this characteristic implies that W value that has area alpha to the left equals n into n plus 1 by 2 minus W value that has area to the right. That is W 1 minus alpha is equal to n into n plus 1 by 2 minus W alpha, and W 1 minus alpha by 2 is equal to n into n plus 1 by 2 minus W alpha by 2. So we can obtain critical values for right-tailed test, left-tailed test, and also two-tailed test. Let me explain this with an example, then only the points will be clear to you. So our hypothesis test is left-tailed, n is equal to 10, alpha let it be 5% equal to 0.05, and our hypothesis mu 157 versus H1 mu is less than 157. Now for n is equal to 10, alpha 5%, W 0.05 is equal to 44. So for in the right tail, this is 44, this is 0.05, 5% of the area. So for a left-tailed test is W1 minus 0.05 is equal to W 0.95 is equal to 10 into 10 plus 1 by 2 minus W 0.95 is equal to 55 minus 44 is equal to 11. So for a left-tailed test, the area is 11. And the decision rule is reject H0 if W less than or equal to 11. In our example, the W value obtained is only 9. So it is in the rejection region. So the null hypothesis is rejected. The null hypothesis is rejected. Rejected means Kansas families on an average spend less on monthly food expenditure. So let me generalize our findings. So Wilcoxon signed rank test. We assume that simple random sampling is taken. Population is symmetric. H0 mu is equal to mu 0. H1 mu is not equal to mu 0, or mu is greater than mu 0, or mu is less than mu 0. All these are possible. Decide alpha. Then compute the value of the test statistics, W. W is sum of positive ranks. Then denote it as W0. Then depending on, for a two-tailed test, this is W1 minus alpha by 2, W alpha by 2. For a left-tailed test, W1 minus alpha. For a right, W alpha. Like that. In our example, W1 minus alpha, left-tailed, critical value is 11. And what we have obtained is 9, sum of positive ranks. So it is in the rejection region. So H0 is rejected. Now, for a symmetric distribution, we know that mean is equal to median. So the test can be based either on mean or on median. And this test is not available in all the softwares. This test is available with the software Minitab. And in the software Minitab, the test is median based. You need not worry about all the calculations. You just decide whether your test is right-tailed, left-tailed or two-tailed. Then you will get the critical value and also the value obtained from the sample. Also, the computer will give you p-value. So on the basis of this, you can take a decision whether to accept or reject a hypothesis. So this is one sample Wilcoxon signed rank test. One sample Wilcoxon signed rank test, and as an alternative to one sample Z or T test. If you cannot assume normality, if sample size is small. The requirement here is the population must be symmetric, and that means population should not be skewed right or left.